For the next couple of sessions, I'm going to turn facilitation over to other folks, besides, not me, some other folks. We're going to be turning up the fire hose just a little bit because these are going to be flash talks. So they're only going to be 15 minutes, and then there will be questions and answer sessions at the end of the flash talks as a group. So to start, the first session is going to be on delayed mortality, which is something a lot of us are seeing out in our forests here 2, 3, 4 years after our wildfires in Western Oregon. Things we thought were going to live are not. It's kind of depressing, but it is the way it's working. Andre Holz with Portland State University is going to facilitate the next section of these flash talks. So Andre's coming up.
Hi everyone, we're very excited to be here to present this session, this very preliminary incipient work that we have here today. We're going to start with Matt Reilly, then we're going to have Alec Dyer, then I'm going to present on behalf of April Hersey, and then I'll close the session talking a little bit myself. And with that, it's all yours, Matt.
Great, thanks for coming out. It's really nice to see everyone. And I first just wanted to start acknowledging my co-authors, Aaron Young and Jeremy. And today I'm going to talk about remote sensing of post-fire delayed mortality, sizing up the elephant in the room. And I think the truth is that delayed mortality is not really an elephant in the room necessarily. There's studies around the world that document that trees continue to die after fire. It's a slow process. There's been a lot of investment in western forests recently, looking at individual trees and delayed mortality over time. But we still really lack information on the magnitude and extent of delayed mortality at landscapes and regional scales. And so in terms of remote sensing, I think delayed mortality is a bit of an elephant in the room. We've heard a lot about these Landsat-based burn severity maps today. It's very, very common. They're a great tool, wall-to-wall coverage back to the early 1980s, looking at spatial patterns and the extent of burn severity. But they're currently limited to really either immediate or one-year assessments, and so they don't capture that delayed mortality. So I have two objectives today, and the first is to describe and validate this method that we've come up to assess the extent and magnitude of delayed mortality, and that work is going to cover fires in Oregon, Washington, and California. And then we just put together some summary results from a handful of fires in the Oregon Western Cascades for a little bit of a local look at what might be happening with delayed mortality. So the method that I've come up with is it's really, really pretty simple. Usually when we make these burn severity maps, we take an NBR value here. This is an NBR value from a single pixel of a Landsat image and how it changes over time. And we usually take this pre-fire value and a post-fire value and difference it, and they correlate pretty well with different metrics of burn severity on the ground. But what this method does is it takes a whole stack of Landsat images, and for 5 years out, it selects the lowest pixel where that NBR value bottoms out, and then composites them for each pixel across the whole fire. And you use that as your post-fire image. And so this is I showed this. One of the potential limitations is that while delayed mortality is happening, we also have post-fire greening, things are growing, shrubs are coming back, and so it potentially is a little bit limited the further out we go where we can see this rebound where NBR comes back up, even though trees may be dying. That may be just a limitation. And so validation for this has been a real challenge. The silver bullet would be some plots that were measured before, immediately after the fire, and then for the 5 years following. And I've been searching high and low for like 3 years now. I have a couple sets. They're not quite the silver bullet I've been looking for, and so we've been relying on this high-resolution imagery to try and validate and give us a sense of whether or not this method actually works and can capture delayed mortality. And so we selected 6 study fires across Oregon, Washington, and California, so quite a broad gradient and biophysical settings. And they basically had to have 1 year post and 5 year post NAPE imagery to look at. And what we did was we took our Landsat pixels and drew a 30 by 30 meter footprint, and then within that we estimated live tree cover and the number of live trees at that 1 year and 5 years so that we could difference them and look at change. And so we do okay. That change, that decline in NBR is significantly correlated with the canopy loss here. It's not as strong as we see with like DNBR and basal area mortality, but we seem to be capturing something. It's just a little bit stronger with the number of trees that died. And so as that decline between 1 and 5 years increases, we see that more trees die. But there's quite a bit of variability, but there's a signal there. So what we did was we came up with a threshold. And so what you see here are sort of the distribution of NBR decline values and whether or not we observe delayed mortality or not. And what we find is if we have this threshold of about 110, if that NBR value declines by about 110 over those 5 years, we have about a 78% accuracy rate in identifying where delayed mortality occurred. And we have pretty balanced omission, commission errors. So we're pretty confident that we can get at that extent question with delayed mortality. This is what some of the maps look like. This is the Dollar Lake fire, north side of Mount Hood. These are some of the other fires from across Oregon, Washington, and California. And then I have just sort of what some of the NAPE images look like corresponding with those patterns of NBR decline. And what really jumps out is that we have these really spatially clustered patterns of this NBR decline. The red is where we have an NBR decline of greater than 200, so that's way past that threshold, and then the white is greater than 110. So yeah, highly clustered spatial patterns, tremendous variability among fires in terms of the extent of how much we see that spectral decline, basically ranging from 20% in these Dollar Lake, Mother Lode, Cascade Creek, those are all, I think, West Cascades fires, to a low of the Yukonom down there in the Klamath Mountains at only 6%. And then Table Mountain is East Cascades of Washington, and Aspen is Southern Sierra. And so moving right along, I've sort of given you a preview of the method. We wanted to just take a look at what things look like in the Western Cascades. And so we selected 7 study fires. Basically, we had to be sure that there was no salvage logging in them because that can sort of mess up our remote sensing signal. And using that same method with NBR decline, we estimate the extent of delayed mortality between that 1 and 5 year period. We compare the distributions, so how are the distributions of burn severity values shifting over time between 1 and 5 years? And then we compare landscape patterns. How did those post-fire dynamics or mosaics change over time? And then we take a really quick look at the extent and magnitude of NBR decline among some different vegetation types. So this is our handful of fires from the Western Cascades. These are all in Oregon. And again, we see quite a bit of variability in terms of the extent of delayed mortality. And so this would be the column way on the right, ranging from about 2% in the Clark Fire. This was a relatively low severity fire at lower elevations in the Western Cascades to a high of upwards of 30% in this Middle Fork complex. Just a glimpse at what the changes in the maps look like. This is the Warner Creek Fire, I think 1991, outside of Oak Ridge, Oregon. What I've done here is I've classified these into, unburned, low, moderate, based on some burn severity thresholds that I've developed for immediate post-fire assessments. And I think when you look at a map like this, it's not overwhelming in terms of what's happening with delayed mortality. But when you zoom in and take a closer look at specific places inside the fire perimeter, you can see there's quite a bit of change. And so on this top here, we can see this patch of moderate severity fire growing quite a bit. In B, down in the bottom right-hand corner, we can see our patch of high severity fire. It sort of gobbles up some of the live residual lower moderate severity patches in the middle and expands at its perimeter. And then C, we have this unburned, very low patch that really decreases in area and shrinks. So something like a fire refuge is really shrinking in this case. And so a couple, just some glimpses, some other ways to look at this Warner Creek fire. These are the distributions of burn severity values. The top is immediate, the bottom is 5 years post-fire. And what you can see is this real shift towards higher levels of burn severity. On the right, this is what's called the Sankey diagram. It allows us to sort of track the fate of individual pixels. And so we can see this unburned very low gets cut in half in this case, with most of that going up to low, a little bit more going up to moderate. And then if we look at the bottom, for instance, you can see that the amount of high severity fire increases by about 7% there. Just a super quick look at some of the other fires. These are kind of the bookends of that variability in terms of the amount of delayed mortality we saw. This Clark fire, again, low elevation, sort of western hemlock, Douglas fir, not much delayed mortality that we could pick up. Warner Creek is the one I just showed you, so you can use that as a little bit of a reference for the magnitude of change. And then we have this Middle Fork fire, which the distribution looks a little bit different than Warner Creek, but we can see, again, this large decrease in the unburned low and subsequent increases in the moderate. And so the next thing we wanted to look at is how are these patterns of delayed mortality or spectral decline affecting some landscape patterns. And so what we did was we took all those fires together, and this is just a size class distribution of the patches of high severity fire. And the big thing that I want you to look at here is that we have this 25 or 30% increase in the area made up of these really, really large patches. So what that means, if you remember Brian's talk, is that seeds will probably have to travel additional distances to get in there and have successful regeneration. So that's some of the implications there. In terms of unburned or very low severity, sort of fire refugia, we see large declines in the area, but we really see these big decreases in the larger patches. And so these fire refugia that can be very important for species like spotted owls and things like that. The abundance of them is decreasing. The patches are smaller, and they're likely more fragmented as well. And then finally, just a last look at sort of different forest types and how delayed mortality might be operating across them. We see a pretty strong trend here in elevation gradient, with almost 50% of the fire that's occurred in the mountain hemlock zone experiencing NBR decline of greater than 110. So that's our threshold for where we see it. And I have a little histogram up there of that 50%. A little less than half of it is really quite high, above that 200 NBR decline threshold. Pacific silver fir, we see a little bit less, but still quite a bit, 40%, that's probably experiencing delayed mortality. And interestingly, our Douglas fir, western hemlock, lower elevation forests, we see only 17%, so far less. In terms of late successional or old growth forests, about 33%, so a pretty big chunk. And again, of that 33%, about a third of that is really at that high level of greater than a 200 NBR decline. And so with that, just some conclusions. The jury is out there, and I'm really interested to see if people are buying this or not. But I think that this NBR composite method, it's capturing something. We're capturing some signal of delayed mortality. And yeah, we need more validation. And I mentioned before, we are working with some plot data with basal area mortality, and are hoping to be able to bring that in, but we haven't quite found that silver bullet yet. So the NAPE is really what we're basing this on at the moment. Extent is tremendously variable, but ranges from 2 to 30%. I think our high elevation forests really appear to be the most vulnerable based on this small sample of West Cascades fires. Implications: smaller, probably more fragmented patches of fire refugia and larger patches of high severity fire, and more loss of old growth late successional forests. And then finally, I think once we can sort of get people to buy in or get this validated and get more confidence, I think it will really open up a lot of opportunities to expand some of the delayed mortality work that's been done on the individual tree level to larger scales. And there's just, I think, a lot of options, refining estimates of old forests and looking at effects of fires on carbon storage and things like that. So just some real quick acknowledgements, funding from the Westside Fire Initiative and the Right Seed, Right Place. And then Jane Curtis has been really helpful. She did some work in the Warner Creek Fire, and Phil and Micah have been sharing some data from the Park Service. And so with that, I'd be happy to take any questions. Oh, okay. All right. I can't believe I got it all in 15